Alright guys, here we have Unit 5, Bonding and Inorganic Nomenclature. A couple folks requested a video on this section from another class, and so I figured I'd put one up, and it'll also give you something to watch since I'm going to be missing Wednesday. I'll try not to breathe into the mic too much. I think I kind of have it out of my face a little bit, but I'll do my best. If I breathe into the mic, I apologize, and we'll see if we can't have some fun. So looking at Unit 5, it's all about creating these chemical bonds and then how do we write them and how do we name them. I'm going to go more into the three types of bonds, and then class we're going to do more about how we name the bonds and things like that. Our first chemical bond is ionic bonds. Ionic bonds are when you have an atom that either gives up or gains an electron, and what happens is you have one atom that gives up an electron and becomes positive. For example, sodium. Sodium's got one valence electron, and so what it's going to do, it's going to lose that electron and get a +1 charge. But that electron's got to go somewhere, and so where it's going to go, it's going to find an electron like group 17. Chlorine has 7 valence electrons. It really wants to grab an electron. It's going to take that electron and become a chlorine -1. So you have sodium that's happy because it lost an electron, and you have chlorine that's happy because it gained an electron. Check it out. You got a positive, you got a negative. What happens between a positive and a negative? Opposites attract. And so you put those two guys together, you get sodium chloride, NaCl. These are ionic compounds. Now, usually we talk about sodium chloride as salt. Now, a lot of times in class, you'll hear me say table salt because I'm being specific about what this is. But really, every ionic compound, anytime one element loses an electron and the other element gains an electron, it's called a salt. So salts are any ionic compound. Another example would be potassium with a polyatomic ion called nitrate, excuse me. And potassium loses an electron, the nitrate picks up the electron, you end up with potassium nitrate. Now check it out. Chlorine was by itself gaining an electron. NO3 is two different elements, nitrogen and oxygen. And so it's something that acts like an ion, but it's actually more than one atom. Check out the name here, a polyatomic ion, more than one atom. So it's a charged group of atoms that stay together. And what's cool about polyatomic ions is that there's a page in your yellow sheet that lists off all of the polyatomic ions, and so you never have to memorize them, and you'll always be able to see what they are and what their charge is. Salts are very hard. Hardness is the inability to be scratched, and the reason they're very hard is because every ion is not just bonded to one other ion, but it's completely surrounded and makes this crystal. And so as long as you have a solid salt, you have this crystalline structure, which makes it very hard, and it's hard to scratch or break, or to scratch but not break. We'll get there in a second. They also have high melting points because you have to break every single one of these bonds in between them to melt them, and so you have to get up to really high temperature to melt. But it kind of seems like it would be opposite. They're hard, they have high melting points, but they're also brittle, because what happens is when you put some force on one of these, you bring one of these positive guys next to another positive guy, and you end up having like charges close to one another, and they can repel and pop off each other. And so this is why a block of salt is going to be hard to scratch, but if you hit it with a hammer, it can shatter into pieces because you're taking positive charges, putting them next to positive charges, and negative charges and putting them next to negative charges. But now, not all atoms want to lose electrons. Everything on the left side of the periodic table wants to lose electrons, and everything on the right side of the periodic table wants to gain electrons. So what happens if you get together two elements that both want to gain electrons? Well, then what happens is you form a covalent bond. Covalent bonds share electrons. So instead of having an exchange, they are going to both share the same electron to get to 8 electrons. So let's look at an example here. Carbon, 1s2, 2s2, 2p2, so you have 4 valence electrons. Fluorine, 1s2, 2s2, 2p5, so you have 7 valence electrons. So every fluorine is trying to get one electron, and every carbon is trying to get 4 electrons. So the easiest way to look at covalent bonds is to draw to draw what's called Lewis structures or electron dot diagrams. This is a vocabulary word for this week, but electron dot diagrams. It's pretty much just a model where you show all of the valence electrons, and you just do it as dots. And that looks kind of ugly there. But 2 shared electrons make a single covalent bond, 4 make a double bond, on and on. We'll talk about that in a second. And not all electrons have to be involved. Yep. So it's easier just to show what this looks like. And the exception to our octet rule is that hydrogen is just happy with only 2 electrons because it's trying to be like helium. So let's look at an example. Carbon tetrafluoride. So let's get a carbon atom. Carbon atom right there. 1, 2, 3, 4 electrons. It wants 4 more. Fluorine atom. Just the X's and the zeros to show you what electrons belong to what atom. So fluorine here has 7 valence electrons because it's in group 17. It wants 1. So what can happen? Fluorine can snuggle up next to the carbon. So now, if you think about each of these elements in a circle, fluorine has 1, 2, 3, 4, 5, 6, 7, 8. We have a happy fluorine. But carbon, 1, 2, 3, 4, 5. Carbon is still not happy. That's why you need 4 fluorines. So you're going to bring a fluorine in on each side of this carbon. We have 4 happy fluorines, and then carbon, whoop, it disappeared. There we go. And then carbon has 1, 2, 3, 4, 5, 6, 7, 8. Carbon is a happy carbon. But now this is ugly. Okay, so what you're going to do, instead of drawing dots or X's or O's for these electrons, you're going to draw lines. And lines represent those 2 electrons that are being shared. And when you really want to get fancy, you just leave all the rest of these electrons off as well and just draw a C with 4 F's with lines going out from it. So we have carbon tetrafluoride, and we'll get to the naming a little bit later. So 4 fluorines surrounding carbon, sharing 1 electron each, so 2 electrons in each of these bonds. Let's look at methane. Same idea, you have carbon, and then you have hydrogen. Hydrogen only has 1 electron, but it's happy with only 2. So you get the same situation. A hydrogen comes in and snuggles up. This hydrogen's happy because it's got 2 electrons. Carbon still needs 3 more, so you get 1 in every other direction, and you end up with methane. Everybody's happy. Everybody's got 8 electrons for carbon, 2 for each of the hydrogens because they can be like helium, and there's 2 electrons in each of these lines. Let's look at something a little bit different. Let's look at nitrogen triiodide. Nitrogen, 5 valence electrons because it's in group 15. 1, 2, 3, 4, 5. Iodine, 7. Just like chlorine, it's that halogen, it's got 7. And so you can kind of even see where these guys are going to fit in right off the bat. The iodine's going to come in. You have a happy iodine. Still need more to make nitrogen happy. Come in and come in. Same idea. You just only need to make 3 bonds to make nitrogen happy because it had already had that extra electron there. And so you have 1, 2, 3, 4, 5, 6, 7, 8 electrons around nitrogen, 8 around iodine, 8 around iodine, 8 around iodine. Now carbon dioxide is where it gets a little bit weird. Check this out. So we still know carbon, we need 4 electrons, 4 more electrons, and then we have oxygen. Oxygen, 1, 2, 3, 4, 5, 6 electrons. So now if oxygen comes in here and snuggles up next to carbon, let's check it out. The oxygen is going to have to share 2 electrons. 1, 2, 3, 4, 5, 6. If it just shared 1, it would be 7. You don't have an happy oxygen. So you share 2, and we get to 8. Now oxygen's happy is sharing 2 electrons. This oxygen also shares 2. This one's happy because it's got 8 electrons. Now let's check out the carbon. 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy. Now that's an ugly drawing, so to clean it up a little bit, just draw straight lines. Notice the difference here. 1 line for a single bond, 2 lines for a double bond. And it needs that double bond because you have to share more electrons to make everybody happy. Covalent compounds we call molecules or molecular compounds. They have lower melting points. Most of your organic compounds. Butter comes from fat, comes from animal products. This is a molecular compound, and so it has a low melting point. It's easy to break. And it always consists of two non-metal elements. For covalent bonds, you have hydrogen, then you have your non-metals. Nothing in a metal can form a covalent bond. So just non-metals. Anytime you have two non-metals, you have a covalent bond. Finally, you have metallic bonds. In metals, the valence shells of atoms are going to overlap, so the valence electrons are free to travel between atoms throughout the material. So let's review what we have so far. We have ionic bonds, where you have a metal that loses an electron and a non-metal that gains an electron. Okay? You have a covalent bond, where both atoms gain electrons because they're sharing. Metallic bonds, both atoms are going to want to lose electrons. And so what happens is the electrons are just free. They can travel anywhere they want to go in a metallic bond. So let's check this out. Insulators, these are covalent bonds. Over here is a covalent bond. The valence electrons are attached to particular atoms, and check out what happens. The electrons have to stay with their atom. It says an insulator. If you hook up a electrical cord to this side and you put your finger on this side, nothing's going to happen because the electricity can't move from one side to the other. Now let's look at what happens in a metal. Check this out over here. Okay, in the metal, the electrons can go anywhere they want to go, and so they fly all over the place. And so that's why if you hook a generator up to this side and your fingers over here, those electrons can transfer from one side to another. You just got shocked. Metallic bonds. All the electrons are free. So let's look at how this happens. Those free electrons make it so you can make wire. The electrons can travel from one way all the way to the other end because those electrons are free. It makes it malleable because the atoms can slide by one another because they're not in crystal form. They're in these forms where the electrons can squeeze and move all over the place. And then you can obviously conduct heat and electricity because of these free electrons, these electrons that are moving all over the place. Now, what's cool about metallic bonds is we don't have to name them. Okay, metallic bonds are just named after the metals they are. So gold or silver or bronze or copper or things like that. So we don't have to give a special name to metallic bonds. So the rest of this chapter is all about naming the metals. There's a few other types of bonds I'm just going to mention real quick. You have some dipole-dipole forces, hydrogen bonds, London departure forces, blah, 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 blah. And once again, I mentioned them very quickly because we don't even know about them. So don't worry about it. All right. Next video I'm going to make is about writing the formulas, so I'm going to end it there, and I hope I didn't breathe into the mic, and if I did, I'm sorry. Love you to death.